complicated than the constant velocity. You can be moving with a constant velocity, but at t equals t2, your velocity suddenly changed into another constant value. So it is still going to be a straight line, but with different slope. This is what the xt graph should look like if your x velocity go from one value to another value, right? So the vxt graph corresponding to that xt graph should be some constant velocity in the beginning. Let's say this is v1x. And then at t equals t2, this velocity suddenly jumps to another constant value. Let's call this v2x. Okay? So in this case, the velocity is changing. If I want to ask what is the total displacement from t equals t1 to t3, I can no longer just use this simple formula because the velocity changed in the middle. What I'm going to do is to just separate this process into two parts. The first part is that from t equals t1 to t2, let's say the change of time here is delta t12. It stands for the time that goes from t1 to t2. Okay? So during this delta t12, the particle has moved a little bit by delta x12. And this delta x12 is easy to calculate because from t1 to t2, the velocity is a constant. So this is the same as what we had before, but we need a little bit more notation to distinguish it from whatever we're going to do next. Okay? Remember, at this part, the velocity of the particle is v1x. Okay? So I can do the same thing for the second part. The change of time is delta t to 3, and during this time period, the x position has changed by delta x to 3. And you can do the same calculation to get delta x to 3, but you just need to use the x velocity for the second part of this particle's motion. And then if you want to ask what is the total displacement from t1 to t3, well, from t1 to t3, you first go up by this much, and then you go up more by this much. So the total x displacement will be the sum of the displacement of these two parts. Okay? And that will be just the velocity of the first part times how long the first part is, and plus the same thing for the second part. Now, the first term, if you look at here, this is t1. Delta t12 will again be the side length of this rectangle, while v1x will be the height of this smaller rectangle. So the first term corresponds area of this smaller rectangle. Okay? Similarly, T3 is at here. This is how much time has passed for the second part. This is how fast the particle is. This is how big the x velocity is at the second part. So this will be delta x to 3. And you see the total displacement will be the sum of these two areas. So it is still the area under this VT curve. Okay? Alright, what's harder than 2? Let's say 3. 3 is harder than 2. Let's do one more example. This time, when the particle is moving, the velocity goes from this big to this big to this big. And let's say you want to figure out the displacement of this particle from T1 all the way to T4. And then you need to pass through all these 3 parts. But again, you just separate these 3 parts into individual constant velocity motion. So the displacement of the particle in this part, delta x, let's say 1, 2, plus delta x 2, 3, plus delta x 3, 4, will be the total displacement that you want to calculate. So again, this thing each of them will be the corresponding velocity. Let me draw the velocity first. In this case, the velocity will be going from one value and jump to another value. And then at T3 jumps to one more value. So if we are looking at the displacement from T1 all the way to T4, the individual part will be the velocity corresponding to that part times the time interval corresponding to that part. And that again will be the area under this curve. Okay? So it seems like we can keep going and keep going. So that. So for any general Vx, no matter how the x velocity is changing with time, if I want to look at the displacement of the particle from some t1 to t2, I can just cut this time interval into a lot of small intervals. I can say that this particle is moving with this velocity for a short time period, and the velocity jumps to another value and moves for another short time period. And then again, 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 again. And then for each small time interval, the displacement corresponding to this, let's call it small delta x, because right now this displacement must be really small, because I'm cutting the time interval into a very small time interval. If you argue that this step-like curve looks nothing like the curve I drew in the back, then I will say it's because I'm teaching, I need to have space to plug in this delta x. In reality, I'm just going to keep cutting it until you cannot tell if a step or a curve. And then they are equivalent, so I can just calculate the displacement from all of these beams and add them together to get the total displacement. Any question? So if I want the total displacement that a particle has moved, I just add the displacement of the first small time interval and the second one and the third one until the last one. I don't know how many n is, but it must be very big. And then what you're looking at here should be the velocity of the first small time interval, the velocity of the second time interval, times the small time interval itself, the nx. And this is going to be, again, the sum of the area under the Vxt curve.